Hi, my name is Matthew Castronuovo, and this is my Physics Lab 3, the black hole. So, an introduction, the purpose of this lab is to model the behavior of orbital motion or just the behavior of a projectile through the force of gravity at a very, very large scale, a planetary scale. So, some important concepts obviously, the force of gravity, which is given by the equation negative g m1 m2 over radius squared r hat, orbital motion, the centripetal force, and F net perp and parallel, which are just the components of force, the net force that change the object's speed, which would be F net perp, or the object's motion, F net parallel. And so the main results you can see right down here. First of all, we have the orbit of our star and the mass of the black hole, and then the trajectory of our ship and the ship velocity that is needed for that. So the experiment, the system in part one was the star and or rather, the system was the star and the surroundings were the black hole. And in two, the system was the ship and the surroundings were the black hole and the planet. The initial conditions for one were that the planet was at, or the star was at, had a given trajectory given by our email, and the initial conditions in part two were that the ship had an initial trajectory that we had to determine. So the experimental details, basically in the first experiment, we just watched the orbit of a star, and in the second, we had to trial and error to see the correct velocity for our ship to escape the black hole. So some model assumptions for part one, the force of gravity is the only thing working on the star, and the force of gravity on the black hole due to the star is insignificant to change the position of the black hole. And in part two, there's no drag force on the motion of the ship, and the only objects in the universe are the black hole, planet, and ship. So here's my first model. The code just utilizes all of the equations we've been learning throughout the semester, really, some position update, some momentum principle, and that all accumulates down to the final where we calculate the mass of the black hole by rearranging the force of gravity equation. So the results, this was the motion of the sun, and the mass of the black hole was 1.03 times 10 to the 34th kilograms. And then my model for the second one looked like this. Again, just calculating the forces on everything using the gravitational equations, adding them because it's force net, and um, updating positions and velocities to show motion. And the results of this were that using the speeds -5 times 10 to the 7th and 4 times 10 to the 6th, the trajectory looked like this, where it goes around the black hole and escapes. So what does this mean? Well, the force is, how is force and its perpendicular and parallel components different from the rate of change of momentum? Well, they are the same quantity, but there are slightly different ways to solve them. So the rate of change of momentum is just going to be the change of momentum over the change in time, whereas force net can be calculated by mass times acceleration. So in some instances, like this lab, it is easier to calculate the rate of change of um, momentum because we know a lot about, we have a small delta time that is given, and we can solve for initial and final momentum. And then what if how can we get our spaceship to orbit the black hole? In the simulation, I was not able to find the correct trajectory to get the spaceship to orbit the black hole. But in theory, it would have a similar velocity to the planet's motion and a similar direction, which is the most important thing. And it would most likely go off of the planet and be have a trajectory out